Hi, my name is Alex Schellebauer, and I work at the discrete computation team here at Wolfram Research. And today I'm going to be discussing how you can enhance your 3D models with subdivision surfaces. In this talk, I'll start by discussing the challenges involved in modeling smooth surfaces. I'll then introduce subdivision surfaces, both how they work and how they can address some of these challenges. After that, I'll explain how subdivision regions are represented and used in the Wolfram language. And finally, I'll wrap up by covering two workflows for working with subdivision surfaces and explore a few practical applications. All right, let's start with the challenges of smooth surface modeling. Polygons are the de facto standard when it comes to 3D modeling. This stems from them being both computationally efficient as well as their flexibility in representing various surfaces. These advantages have led to both GPUs being optimized to render them and a significant amount of 3D modeling software to be based around them. Unfortunately, there's one major downside to using polygons for everything. That problem is that reality is smooth, while our polygons are not. Most objects we encounter in everyday life contain some curved surfaces, whether they be natural or man-made. Even things we think of as flat will often have rounded corners when you look closely. This introduces a problem, as the polygons we use to model these continuous objects are fundamentally discrete, and therefore we can never accurately capture most objects using polygons. So, how do we handle this in practice? Well, we just use more polygons. As we increase the number of polygons, our mesh better approximates the smooth surface. Eventually, we reach a point where it's good enough for rendering. We can also use some shader tricks to smooth normals across the polygons, or to remove that sharp line transition across the different faces. However, just adding more polygons is not as easy as it sounds. Even with powerful editor tooling, manually adding more polygons to increase smoothness is a tedious and time-consuming task, especially as the complexity of the model grows. In addition, doing this by hand essentially locks down our model, so any high-level change becomes a major undertaking, requiring thousands of edits. For example, it'd be easy to make a change to, let's say, the leg or the ear of this hippo on the leftmost model with very few polygons. But that same change on the rightmost model over here with over 20,000 polygons will be much harder. So, is there any way we could automate this process? One potential answer is splines. In contrast to polygons, splines are fundamentally smooth and can perfectly represent curves and smooth surfaces. You'll often see spline curves used for things like font, while spline surfaces, like NURBS, are common in CAD applications. Without diving too deep into the details, the basic idea of splines is to have some structured grid of control points. For curves, it's just a 1D array of points, while for surfaces, it's a 2D array. Each point on our surface is on some weighted average of these control points. By changing a small number of control points, we can easily make high-level changes, particularly in comparison to having to move every point manually. For example, with the spline curve on the right, I can just change a few of these red control points to drastically change the overall shape of the curve. To do something similar with the traditional method, I have to manually move every single point on this curve here. And even then, after all this tedious work, it's not going to be as smooth as the spline version. So hopefully this helps demonstrate how powerful splines can be. Furthermore, splines are well parameterized. So while we can't render them directly, it is easy to convert them to polygons for rendering. We can simply choose how detailed we want it to be and let the computer handle the tedious refinement. So this is all great. We can model perfectly smooth surfaces with high-level control and then automate the conversion to polygons. So what's the catch? Well, the advantages of splines all come at the cost of ease of modeling. When modeling surfaces using something like NURBS, you need to break the surface down into rectangular patches of control points. This can make modeling objects with certain topologies particularly challenging. On top of that, it can be tricky to ensure neighboring patches line up with one another, and they both cause discontinuities if they don't. These problems explain why splines are less common in 3D modeling. Instead, many people use a technique that keeps most of the advantages of splines while still being easy to use. And that technique is subdivision regions. So what are subdivision regions? Well, they are regions constructed by an iterative process that creates smooth meshes from coarse ones. In the context of 3D modeling, we tend to use the phrase subdivision surfaces instead, though the same idea can be applied to curves as well. As I said, this is an iterative process, and each iteration involves two steps that we apply to every polygon in the mesh. The first step is to subdivide the polygon into smaller polygons. This step doesn't actually change the shape of our mesh, but instead provides us with more polygons to work with. The second step is where we actually change the mesh's shape by moving vertices to be some weighted average of those in their local neighborhood. Now, details of exactly how polygons are subdivided and smoothed is determined by the subdivision scheme. Different schemes are often optimized for different polygon types, such as Catmull-Clark being meant for quads, Loop for triangles, and as the name suggests, quad-tri for a mix of both. Here we can see some examples of how different schemes subdivide a single polygon depending on the number of sides it has, such as a triangle, a square, and a pentagon. Now let's look at what happens when we apply an iteration of a scheme to all polygons of a mesh. We'll often refer to the result of applying a certain number of iterations as a subdivision level, with level 0 being the original base mesh. As this level increases, our mesh becomes more and more smooth. As the level increases, it converges to a specific surface that we call the limit surface, shown here on the right. Unlike the previous finite subdivision levels, this limit surface is continuous and mathematically smooth, like the spline surfaces we saw earlier. In fact, they're not just like splines, but actually equivalent to splines, with the exact type of spline depending on the subdivision scheme used. Through this lens, we can think of the vertices in the original base mesh as the control points, and the base mesh itself as a control mesh, also called the control cage. So, with this new insight, we can compare the two modeling methods. Here we see that subdivision regions provide us with most of the benefits of spline regions, such as being mathematically smooth, having high-level shape control, and being easily convertible to polygon meshes with different resolutions. But in addition, there's also much more robust to different topology. Because of this, subdivision surfaces are often viewed as generalized splines. Now that we have some understanding of subdivision regions, let's look at how they're represented and used in the Wolfram language. We represent both subdivision curves and surfaces using the subdivision region symbol. To get a specific level of some base mesh, you can give that mesh and a desired level, and the result will be the subdivided mesh. So here we see the first subdivision level of our base mesh, where it's rounded off some of those sharp corners. We can continue this by increasing the level, and see our mesh becomes smoother and smoother, slowly approaching that limit surface. However, if we actually want to represent that limit surface exactly, we can use a syntax where we omit the second argument and just pass in our base mesh. This will represent the perfectly smooth limit surface and not one of the finite approximations that we saw earlier. The syntax is also equivalent to explicitly specifying a subdivision level of infinity, as we can see here. All right, and to specify a subdivision scheme, you can pass in its name as a string. For example, this code will give me the second subdivision level of the mesh using the loop scheme, as we see here. Currently, we just support three schemes for surfaces in 3D, which are Catmull-Clark, loop, and quad-tri. We can see there are different effects on our tetrahedron below. Now, these schemes can produce significantly different results for small meshes, like this tetrahedron. But as you can see, the differences become much less pronounced for more complex meshes, like this hand. So in practice, you don't need to worry too much about which scheme you're using, because for most modeling, it won't make that big of a difference. Now let's move on to some subdivision workflows. There are two general ways you might work with subdivision regions. The first is as a mesh processing operation, and the second is with control mesh modeling. Starting with the first here, we can treat our subdivision region as a mesh processing operation. These mesh operations take a mesh as an input and then return a processed mesh as an output, typically as a one-time action. In version 14.3, we saw the introduction of a few such operations. For example, we have simplify mesh, which reduces the polygons in the mesh while retaining its shape. We have remesh, which changes the size and shape of individual polygons to be more uniform. Then we have smooth mesh, which reduces noise introduced from things like 3D scanning. So the idea here is we can treat subdivision region as yet another operation, where here it takes in a rough mesh with sharp corners and then rounds them off. An example of this workflow would be to apply subdivision to a mesh, like this ring here, to produce a smoother, more refined mesh as an output, as we can see here. Now this works well enough, especially if you want to just quickly smooth an existing coarse mesh that isn't too detailed. However, the second workflow tends to be a much more powerful use of subdivision regions. The second workflow is that of control mesh modeling. Here you treat it more like spline surface modeling, where we make all of our edits to a base control mesh. Subdivision can then be applied as a post-processing effect to generate the smooth surface. This is very common in 3D editors, where you can even set the subdivision level for different view modes. For example, you can use a low level while modeling and rigging a mesh to let you quickly see the changes, but then use a higher level come render time to produce those perfectly smooth surfaces. As a small additional benefit, when using the control mesh approach, you only need to store the base mesh, since subdivision is deterministic. This means file sizes can be orders of magnitude smaller than if you try to explicitly store the mesh at full resolution. One caveat with this workflow is that it works best when you have a mesh editor with a graphical user interface. This is one reason why we're currently developing a lightweight mesh editor written entirely in Wolfram Language for the function repository. Here you can see some rough edits I made to a base model of a horse using this editor. I start by adding some basic wings, then followed by a horn. And yes, I'm certainly no 3D artist. What I want to highlight here is that the top row shows the control mesh that I edited, while the bottom shows the final subdivided result. Notice how my updates only add a relatively small amount of polygons. Meanwhile, that small amount of polygons then gets automatically translated into hundreds or even thousands of new polygons in the final render. This is the real advantage of using subdivision surfaces when modeling. In the last section for today, I'm going to discuss some applications of subdivision regions. The first is product rendering. Digital rendering of products for use in marketing materials provides a lot of advantages to traditional photography. It allows companies to showcase products in any environment, lighting condition, or configuration, without the cost and logistical headaches of physical shoots. However, the catch is that the product models need to be extremely high fidelity in order to hold up to customer scrutiny. This is where subdivision surfaces come in, since they allow us to generate smooth surfaces at an arbitrarily high resolution. In this example here, we start with a fairly low resolution computer mouse that we then subdivide and style into a high fidelity model. Once we have the model, we can then of course render it with any view angle, lighting setup, or material. We can then take that render and insert it directly into marketing material, like a hero section on a website shown here. Our next application is level of detail, or LOD, generation. When it comes to rendering, the more triangles we try to render in a single frame, the longer that frame will take to render. This means for real-time rendering applications, like video games, it is vital that the number of triangles being actively rendered stay as low as possible. A common way to achieve this is using LODs. Here the idea is to create multiple instances, or levels, of a single 3D object at different mesh resolutions. We can then use the smaller levels when the object is far away, since the extra detail wouldn't be visible anyway. This maps nicely onto our concept of subdivision levels, since we can automatically generate higher resolution instances of a base mesh. In our example here, we have this coarse teddy bear mesh that will act as our lowest resolution level. We can then generate two more levels by using subdivision region. Now, the differences between these meshes is pretty obvious when viewed at the same size. However, if you view them from different distances to the camera, it becomes much less apparent. Despite this, the lowest level on the left uses far fewer triangles than that of the right, which translates into much faster render times. Our last application is animation and simulation. Subdivision surfaces are the standard for these types of use cases where we deform meshes. This is in part due to their robustness, which allows them to appear nice under deformation in places where other representations, like NURBS, might show visible cracks or discontinuities. While they're probably best known for their use in keyframe animation, such as every Pixar film since Toy Story 2, subdivision surfaces can just as easily be used in meshes deformed via physical simulations. Here I have a simple cloth simulation I wrote using the Wolfram compiler. After running it, we'll see two different views. On the left, we have the underlying sample points of the cloth that were simulated. I can go ahead and step through a simulation and we see they fall and wrap around our sphere. Now, ideally, we use as many sample points as possible, but that comes at the cost of increased simulation runtimes. So instead, we can use subdivision surfaces on this deformed grid of sample points to make a more convincing cloth, which you see here on the right. So I can rotate this around and we get a nice, realistic looking cloth from a much sparser sample set of points. All right, to wrap up this discussion, let's compare the use cases that are ideal for subdivision surfaces and those that are not. The ideal use cases include 1, modeling smooth surfaces, such as animals or products. 2, when adapted mesh fidelity is needed, such as with LODs. 3, we have animated or deformed meshes, like we saw with the cloth simulation. And lastly, 4, to use as a mesh processing operation to round off simple meshes. In contrast, subdivision surfaces are not ideal if you require precise measurements and curves, as is common in CAD applications like mechanical engineering or architecture. Non-manifold meshes can also pose a problem for subdivision surfaces. While they may be more robust than splines at handling tricky topology, they still have some basic requirements. Therefore, they're not a good candidate for handling so-called triangle soup. And finally, subdivision is not ideal for smoothing meshes that already contain a lot of polygons. This is due to it intentionally limiting the area of effect of a single vertex in the base mesh to only the nearby polygons. So if your mesh is already high fidelity, the subdivided surface will look very similar while using many more polygons. And that concludes my talk. Thank you for listening, and I hope you'll find your own use cases for subdivision surfaces. If you want to learn more about mesh processing in general, I recommend watching my colleague Jablem's talk here on the new mesh processing features added in the latest version of the Wolfram language. We also have a YouTube channel at WolframRD with content related to new functionality we're adding. So please check that out if it sounds interesting to you. All right, we have some time now for questions. So if there's anything you'd like to ask, please open your Q&A tab and type it in there, and I'll do my best to answer it. All right, I have one question here from Patrick. Wondering if you have attempted to use LiDAR on iPhone to generate models for use in Mathematica. I have not done that personally, though we do have some functionality now where you can take a plane cloud that could have been generated from a 3D scan and convert that into a mesh. That's done with the reconstruction mesh function, which I can pull up here, the documentation at least. Yeah. So for this function, if you have a plane cloud brought in from some 3D scan, you can just give it the points, and it'll estimate whether it's, for example, a curved surface or solid, and it will use whatever method it thinks is best to rebuild that surface. So it's something you could achieve if you have that plane cloud already scanned. All right, another question here from Eve. Can you share the YouTube and contact info in the chat? So yes, let me just find that here. The YouTube channel, Wolfram RD. All right, let's add that to the chat so you should be able to see it now. Next year, how long have subdivision regions been around as a concept? They've been around for quite a while, at least a couple of decades. I think they started getting big in the late 90s, especially for like actually animated films. I think Toy Story 2 is like one of the first famous uses for it, like a feature-length film. Yeah, so they've been around for a while, so they're tried and tested here. All right. Another question from Les. This is a hypothetical. What would you start with for a blood vessel network or plant root system? This seems like more of a general question. Trying to think. For that, you could do something where you create a random point cloud sampled from some region, and you use one of our graph functions. For example, there's like a find spanning tree, which you could sort of start with a certain point, and it'll find a path to all the other points to connect them all. So maybe stuff like that could be useful for that type of, it seems like procedural generation. Yeah, I'll give it a couple more minutes here for any other questions to come in. All right, another question here from Harold. Would you use smooth mesh and related functions to start a finite element PDE analysis? So I think it's definitely would be one use case for smooth mesh, especially the remesh function. That really helps with getting rid of some of those problematic triangles. I haven't done too much finite element analysis myself, so I'm not too familiar with the workflows, but I think it'd definitely be a use case you could do for it. All right. Les asking again, what was the spelling of that mesh command? Not sure which mesh command are you referring to? We have the kind of mesh processing operations here. If you could maybe reply again more specifically. And then as far as the root system and stuff, for that I was referring to find spanning tree, something like this, which can be good for when you have kind of a network of your points, you can find a single tree that connects them all. All right, and a question from Tim here. Is any type of mesh deformation on the horizon? Potentially, nothing right now, I believe. That would be something we'd like to be able to do. Just getting better at deforming meshes and even doing stuff like bone weights would definitely be a nice thing to add. All right, seems like the questions are slowing down here, so I'll probably close this talk. If you think of anything else, I'll be in the office hours for geometry tomorrow at 1:30. So feel free to join in and ask your questions there. All right, thank you very much for watching, and I'll see you there if you want to join.